Hello APC Mechanics students, today we'll solve the past paper FRQ 2023 Set 2, Exercise 1. Then skipping the directions and starting directly by the exercise, remember that the figure always happens to be above the text. Scientists have created a new type of lightweight foam and are performing experiments to investigate the properties of the foam. The mass of the cart A is 1000 kg. Remember that the inertia of the object is important for us. And the mass of cart B is 2000 kg. A piece of foam with negligible mass is attached to the front of cart A as shown. Cart A moves with a constant speed toward cart B, which is initially at rest. At time t is equal to 0, the foam connected to cart A makes contact with cart B. The foam remains in contact with cart B for 0.5 seconds, after which the carts separate and both carts move with constant velocity, which means that collision between carts A and B happen, with the foam being in between. If you check the first page, we don't have any questions. Then let's proceed to the next page. Now part A, the graph shows the velocity v of cart A as function of time for the time interval when the foam and cart B are in contact. This is important for us. Remember that a trick in the AP curriculum is to give us the variation of quantity, but sometimes the quantity itself might be a vector or scalar. Here in this case, they're plotting the velocity, which is the vector quantity of cart A. In idea number 1, they're telling us what features of the graph could be used to estimate the displacement of cart A during the collision. This is reasonable because this is a VT graph and V represents the velocity, and we know that the area under the curve basically represents the displacement. Then let me say the area under the curve. Now, in idea number 2, they're telling us using the information shown in the graph, determine the speed of cart B at t is equal to 0.5 seconds. Now, usually whenever the exercise is splitted into idea 1, idea 2, idea 3, this means that they are correlated to each other, but this is not always, it's not always the case. So you should be smart enough to know what you should do. They're telling us to determine the speed of the cart B at 0.5 seconds. Remember that this represents the variation of the velocity for cart A and not cart B. And how can we determine the speed of the cart B from cart A? This is done using conservation of momentum because they will collide. And because this is a big law, we need to mention apply conservation of linear momentum. Which states that the initial linear momentum of the system is equal to the final linear momentum of the system. Initially, what do we have? We have only the momentum due to the cart A, which is VAMA. Or let me say MAVA. And finally, both carts are in motion, so let me say we have MA V prime A plus MB V prime B, and we're interested in determining V prime B, which is basically the velocity of the cart B after the collision at t is equal to 0.5 seconds. Now the mass of A, if you recall, is given by 1000 kg and the mass of B is given by 2000 kg. So let me write here that we have 1000 multiplied by the velocity of the cart A before collision. Before collision it's given by 5, so here at t is equal to 0 seconds, they didn't collide yet, which is also equal to 1000 multiplied by V prime A, which is the velocity of A after collision, which is given by 1, plus the inertia of the cart B, which is 2000, multiplied by V prime B, and we're interested in determining V prime B. Now this is 5000 and this is 1000, which means that 2000 v prime b is equal to 4000, which means that v prime b, which is the velocity after collision, is given by 2 meters per second. And here in this case, the velocity and the speed, they are the same because they are positive. So that's the answer for idea number 2. Now in idea number 3, they're telling us on the following grid, draw a smooth curve of the velocity of cart B as function of time. Initially, we know that the cart B is at rest, so we should start the curve from here. And finally, the final speed of the cart B, or the velocity, is given by 2 meters per second. The curve should end here. In agreement with the shape of this curve, we should connect the initial point and the final point. And after cart A starting losing some velocity, cart B will start gaining velocity until reaching a final velocity of 2. So the curve should look something like that. Alright. Now going on to the next page, they're telling you between 0 and 0.5 seconds, the velocity of cart A can be described by the function which is cubic. And here let me make some comments. Because the velocity is given by cubic, the kinematics basically given by uniform motion and uniform varied motion, they break down because they only work whenever the velocity is linear, which means uniform varied motion, or constant, which means uniform motion. So in this case, if we need to determine quantities related to V like displacement or acceleration, we need to use calculus. In idea number 1, calculate the magnitude of the maximum net force acting on cart A during this interval. And we know that if we have the velocity, we can determine the acceleration. From the acceleration, we can determine the force using Newton's second law, which is given by F is equal to ma, and that's given by Newton's second law. Now, but the thing is that first we need to determine the acceleration, and the acceleration is determined from the velocity via calculus. So let me say that A, which is equal to V prime, which is the derivative of 64 t cubed minus 48 t squared plus 5. Now here we drop the power, we multiply it by 64 and reduce the power by 1. Similarly here, that would be 192 t squared minus 9060. But if you notice carefully, we're not interested in the force, but rather the maximum force. So we need to find the maximum acceleration. How we can determine the maximum acceleration? Simply we derive the acceleration, we solve for the acceleration is equal to 0, and we substitute back in the acceleration because we're interested in determining the maximum acceleration. So the maximum and the minimum values of a function can be determined by their derivatives. So A prime in this case is given by the derivative of this, which is given by 384 t minus 96. And if you notice that this is a linear equation, we only have one solution, and this is given by t equals to 96 divided by 384, and that's equal to 0.25 seconds. This could be a minimum or a maximum value, but since it's the only solution and we're asked for the maximum, then the maximum value of the acceleration happen at 0.25 seconds. So we now need to compute A max, which happens at t given by 0.25 seconds. Now we replace time by 0.25, that would be 192 into 0.25 to the power of 2 minus 96. Multiplied by 0.25, and that would give us minus 12 meter per second square. Now we're ready to calculate the maximum net force. So I will say that F net max is equal to the mass, which is ma, multiplied by A max, and this is promoted using Newton's second law. Now the mass, if you recall, it's given by 1000. And because we're interested in the magnitude, so I will take the magnitude of the acceleration, which is given by 12, and that would be 12,000 newtons. Then F naught exerted by this collision max on the cart A in magnitude is given by 12,000 newtons. Now in idea number 2, they're telling us on the following grid, draw a smooth curve of the magnitude of the force acting on cart A as a function of time. Clearly indicate the value of the maximum force on the vertical axis. Now, the maximum force achieved during this collision is given by 12,000. Accordingly, let's label the curves. So if this is 2, 4, 6, 8, 10, so let me say this is 2, 4, 6, 8, 10, 12. So basically this is 12,000, let me say. Or fine, you can just label it here to be 12,000. Then the force should reach a maximum value of this one at a time given by 0.25 seconds, which is here. Now initially at t is equal to 0 they didn't collide, so there is no force exerted on A, so it should start at 0, and finally the collision ends at 0.5 seconds, so here again it should drop down to 0. So we expect the curve should increase something like that, then decrease something like that. And remember that the graph of F versus T during collision throughout the course, we remember that they have the following shapes, for example, or the following peaks. So it's reasonable to have the following shape. And if you notice carefully, the form of the acceleration is given by quadratic. Notice that we're plotting the force, not the acceleration, but it's fine, they are related to each other by just a number. So it's given by 109, the acceleration, let me state it here, the acceleration is given by 192 square minus 96t. Now what's the shape of this curve? This is a parabola. Here, because it's not given in the perfect square, so we expect that it won't be located at the origin. Also, you can use a graphing calculator to assist you in order to plot the following. However, we know that the shape of the curve is gonna be something like that. And ending up at 0. Then this is it for idea number 2. Now part C, which is the last part of this exercise, they're telling us the foam is removed from the front of cart A and the experiment is repeated. The carts collide with both cart A and cart B having the same initial and final velocities as in the original collision. So basically we're repeating the exact same experiment, but now the foam is removed. The time intervals during which the carts are in contact are different in the collision with the foam and the collision without the foam. In the collision without the foam, cart A is in contact with cart B for a shorter duration than in the original collision when the foam was present. So basically we're repeating the same experiment, but we're gonna remove the foam. We will have the same initial velocities. What's gonna happen? The same initial velocities and the same final velocities. What's happening in this case, that the time for which cart A and cart B is in contact is much smaller. For the original collision, when the foam is present, the magnitude of the average net force exerted on cart B is given by F1. For the collision without the foam, the magnitude of the average net force exerted on cart B is F2. Part C, what is the relationship between the magnitude of the average net force F1 exerted on cart B for the collision with the foam and the magnitude of the average net force F2 exerted on cart B for the collision without the foam? So we're asked to compare F1 and F2, F1 with the foam and F2 without the foam. The thing is that, if you remember, we're talking here about the average net force, and the impulse is given by, for average force, F average delta t. Because we didn't change the initial and the final velocities, the impulse would be the same, which is the change in momentum. Here we're talking about the impulse exerted by A on B or B on A, which they are the same for both. So we will assume that this quantity is constant. Now the thing is that if delta t decreases, what will happen? That F average will increase. Remember that without a foam, in this case, the duration decreases, so delta t decreases, which means that F2 will increase. And in this case, the correct choice would be f2 is greater than f1. Now let's justify. We will say since initial and final velocities are the same, then delta P is the same for each cart. And according to the impulse momentum theorem, J is given by, so J is the impulse is given by delta P, which is F average multiplied by delta T. Remember that the impulse is given by the integral of F dt, and this also can be written as F average multiplied by delta T. So because delta P is the same, which means that J is the same, then as delta T decreases, F average increases. And that's it for me in this video, guys. See you soon in a new one.